There we go. Okay. I know the concentration of lead and I know the concentration of iodide. So I just got really excited and I wrote my Q and I stuffed everything in. And I didn't even bother to look and say, oh, look, the student mixes equal volumes. Yes? I think I actually did this correctly with my block 4 yesterday, but I definitely did not do it correctly this morning with block 2. All right, so because I'm mixing equal volumes, what happens to the concentration when I mix equal volumes? Do you guys know? Yes. It gets divided in half. Yes? Would anyone like me to prove that or show you why? No. Okay. So when we mix equal volumes, the concentration divide by 2. Because we're doubling the volume, the concentration gets halved. So this is going to actually become 0.001 molar lead, and this is going to become 0.002 molar iodide. And our Q then is going to be concentration of lead times concentration of iodide squared, and it's going to be squared because of course our equilibrium looks like this with a coefficient of 2 in front of the I minus. So now when we plug those in, 0.001 times 0.002 squared, we get 4 times 10 to the negative 9. Okay? And I think if you do it wrong, I think you get C, maybe. I don't know. Anyway, I did it wrong this morning and I got the wrong answer, so. All right, so we had 52. We wanted, well, probably. I don't know for sure, but I know 52 should be A. Yeah. Okay, well, that is wrong. But yeah, the answer should be A. And for anyone who came in late, we said that number, what was it, 63 needed a correction. It's 0.25 moles and not 25 moles. The question doesn't work with 25 moles. That would be ridiculously concentrated. And now we are going to look at number 105. So we want to calculate the concentration of iodide ions in a saturated solution of lead iodide. Since lead iodide is the only substance mentioned, we have to assume that is a dump and stir type question. So we are going to have then PbI2 dissociating into Pb2 plus 2I minus. And if I want to know something about the iodide concentration, I'm going to say let X be the concentration of PbI2 saturated, which of course is the solubility. And so that means that this concentration is going to be X, but it doesn't really have a concentration. And this is going to be X, and I is going to be 2X. So what we will do then is we will say that our KSP, this is a 1 to 2 ratio kind of compound. Yes, it's PbI2. Do you know what KSP is equal to? The quick way. 4x cubed. If you don't know that, that's totally fine. You'll just take a little bit longer to do the question because you'll actually have to say, okay, my KSP is equal to lead times iodide squared, which is going to be x, times 2x squared, which is equal to x, times 2 squared is 4, x squared is x squared, which gives us 4x cubed. If this was a written response question, you would want to show most of this. You know, if you skip this step here, that would be okay, right? But you want to show the plugging in and getting to 4x cubed. But for multiple choice, if you know this, you don't have to do all that extra work, okay? So if we want to solve for 2x, first of all, we need to solve for x, yes? So we're going to have x cubed is equal to KSP divided by 4, yes? So x then is going to be equal to the cube root of KSP divided by 4. So x is equal to, well, what's KSP divided by 4? You know what? It's actually easier just to do it this way. I don't know. KSP is 1.39 times 10 to the minus 8, and we're going to divide that by 4. .48 times 10 to the minus 9, and then x is equal to the cube root of that. .51 times 10 to the minus 3. And that is the, whoa, where'd it go? Okay, so that's x. We want to know the concentration of iodide ions, and the concentration of iodide ions is 2x. So the concentration of iodide then is equal to 2 times 1.51 times 10 to the minus 3, which is 3.03 times 10 to the minus 3 molar. And that's probably a typo, I guess. Yeah? So, should be B. The closest answer. Typo. If you're wondering why I do that, it's so when I go through my notes later, I'll see that big star and know I have to make a change in my actual document. Oh, look, typo. Okay. Anything else? Yes. 56. Yes, we could. Consider the following equilibrium system, which would result in more lead iodide dissolving. What if we added more lead iodide? I have a saturated solution because I'm at equilibrium. And if I'm in equilibrium, it has to be saturated. If I add more of the salt, will more of the salt dissolve? No, because it's already full. Wrong. Increasing the pressure. Well, there's no gases. How about adding some lead nitrate? That would increase concentration of lead, and it would also increase concentration of nitrate, but we don't care about that, it's a spectator. That would cause this to shift to the left, which would mean that less of the solid is dissolved. But what if we increase the temperature? The system would shift right to absorb the excess heat to bring the temperature back down. Okay? I'm holding off on number 13 because I want to do a little bit of acid and base first, because I'm not actually going to ask you a question like that one on this test, because it assumes that you know acids and bases, which you don't yet, or at least you won't until after today. Okay? Yeah. So I'll come back to number 13 later. Other questions? Moving on to acids and bases then. Excellent. So we are on 4.1F, except that we're actually going to do a little bit of preamble to that. And I'm just going to print this really quickly for myself so I remember it. I should have done this at lunch, but I forgot to. I do not want to send it to OneNote. I want to send it to the science printer. So first of all, what is a Bronsted Lowry acid? And this is just off script, okay? So I will post this later, okay? This is just going over 4.1A through E, which you should already know. There's no actual sheet for this, okay? Just reviewing 4.1A through E. What is a Bronsted Lowry acid? Tell your partner. This is not on a sheet. A Bronsted Lowry acid is a, starts with a P, proton donor. Now, what do we mean in acid-base chemistry when we say proton? Yeah, a proton, when it comes to acids and bases, means a hydrogen ion, because if you imagine a hydrogen ion, how many protons in a hydrogen atom? One. So we have one proton, and we have, zooming around the outside, one electron. If we remove the one electron, what are we left with? This is an H atom. This is an H plus ion. What's the only thing that's left? A proton. Yes? That's why we refer to an H plus ion as a proton. So if a Bronsted Lowry acid is a proton donor, what is a Bronsted Lowry base? A proton receiver or a proton acceptor? You cannot have one without the other. You must have both a Bronsted Lowry acid and a Bronsted Lowry base, because if somebody's donating a proton, they need somebody to take it. If you're taking a proton, it has to come from somewhere, yes? You cannot have one without the other, i.e. must always have a Bronsted Lowry acid with a Bronsted Lowry base. So let us look at a Bronsted Lowry acid in water. And you use HF because it's easy to write, it's short. A lot of acids have long formulas, this one's short. If I put it, it's aqueous. If I put it with water, what do I get? If HF is acting as the acid, it must be donating its proton to water. And water is acting as the base, and it is accepting that H plus ion, the proton. Yeah? What does HF turn into when it donates its proton? What does it become? If I remove a hydrogen from HF, what am I left with? I'm left with F, but I'm not only removing a hydrogen, I'm removing an H plus. So I'm also removing a positive charge. So what am I left with? I'm left with F minus. Yes, because I took away a positive charge. Now water is going to have an extra H plus on it. So what will its formula become? Instead of H2O, it will become H3O. And it didn't just gain a hydrogen, it gained an H plus. So what will its charge become? Positive. Yeah? Do you remember what the name of this H3O plus ion is called? That is called the hydronium ion. And it is what really happens in water. Do you remember how we were showing the dissociation of acids in the past unit? Right? And we used to show, we would be like, HF, oh, what does it do? It dissociates into H plus and F minus. That's not reality, okay? This is what I like to call the shorthand version. I realize that I'm using a word here and I almost used a cursive letter, so I'm like really showing my age. You guys probably don't know what shorthand is, do you? Do you know what shorthand is? Yeah? How many people have no idea what I'm talking about, shorthand? Okay, shorthand, back in the olden days, people used to dictate, like business people would dictate just like what they wanted to say in a letter to someone or something they wanted just recorded, written down. The secretary had to write really, really fast. So they used a system of little squiggles and like symbols that represented syllables and words, so they could write very, very quickly. So it was almost like learning another language. Yes, but it allowed you to take down notes very, very quickly so you could transcribe what the person was saying very quickly. And that was called shorthand, okay? It's sad that we don't know what it is anymore because the shorthand version is the best way I can think of describing this. It's not a simplified version because it's not reality. This is shorthand. It's not really what it is, but we use it. We very often will just use it like this because it's convenient. It's easy to write. This version up here, though, this is the reality version. This is what actually happens. So we have reality, and then we have shorthand. The reality is that an acid doesn't actually dissociate. What it really does is it ionizes. However, you will hear us refer, you will hear me refer, you'll hear all sorts of chemists refer to the process of acids producing, you know, the acidic solution as dissociating, right? Even on the table in your data booklet, you'll notice that, do you see H3O plus there, anywhere there? Do you see those things reacting with water? No, we use that shorthand version here as well, okay? For our reverse reaction, because this is an equilibrium, for our reverse reaction, who would be the acid? And again, we're going to look at our non-shorthand version here. Who would be the acid in the reverse direction and who would be the base? Tell your partner, and then I'll come back to you. Who's the acid in the reverse direction? Who's the base in the reverse direction? Yes. Yeah, H3O is the acid. In fact, it has to pretty much be the acid, yes, because it's the only one that has a hydrogen. You cannot be an acid if you don't have a hydrogen to donate, okay? And that means that fluoride is the base. And when we're going in the reverse direction, the hydronium ion gives a proton to the fluoride ion, and then we end up with the reverse process happening, okay? When a Bronsted Lowry acid donates its proton, it turns into its conjugate base. So HF donated a proton, and it turned into what did it turn into? F minus. So F minus is the conjugate base of HF. When we use the term conjugate, we mean that the two are related to one another. Yes? So the HF is related to the F minus because they differ by only one H plus ion. Together, when we refer to them together, we call the two of those a conjugate acid-base pair. Okay? And if you want a definition for that, it is a pair of chemical species that differ by a single proton. And what is a single proton? What do I mean when I say that? H plus, yes. Okay? So, HF and F minus are a conjugate acid-base pair. F minus is the conjugate base of HF. HF is the conjugate acid of F minus. And we are going to pop back to 4.1F and then come back to these freestyle notes, okay? Just for a moment here, because there's some stuff in there that I would like to cover, but I'll give you a moment to finish writing. And don't worry, if you don't copy it down, these notes will be posted. Yes, indeed. This is how I always used to teach. It was so relaxing. I just would like talk and write. There was no like hours of preparing documents and nonsense like that. Chem 12 was my favorite course because it was like you just wind me up and I would just go, oh, oh, oh. But now we have to fit more into less time, so there we are. What can we do? Anywho, so much. You can fit more in a linear system because you actually have more time in between things. So like, for example, like you get twice as many weekends, right? You don't like to practice things. So you don't, yeah. And then this business where we have a class on Tuesday, but not on Wednesday, or sorry, a class on Wednesday, but not on Tuesday, you lose an evening in there as well, right? Like it, anyway, and you're losing, because of flex, you're losing 13% of our class time. We are not going to make it to Unit 5. I'm just letting you know that right now. That's electrochemistry. If you are going on to take sciences at university and you will be taking chemistry, I will provide you, if you wish, with all of my notes and handouts and Tyler DeWitt and let's see, Tyler and Mr. Colger can very effectively teach you electrochemistry, say over the summer if you wanted to do some self-study so you don't walk in and be like, I don't know nothing about no electrochemistry. Yes, because that would be a little scary. My AP students have learned it virtually all on their own because they have to finish by May 2nd and we start in February. I hate the semester system for AP in particular because it just doesn't make any sense. It doesn't. Anyway, whatever. So there we are. If you are interested in that, let me know and I will provide you all the resources that you could possibly need. And if you're like, I'm not taking chemistry at university, I don't care, then you just don't have to learn it. You can be like, hey, that was cool. All right. So, where were we at? We were going to 4.1F. So let's just do a little bit of practice here. If we have a Bronsted acid, sometimes Bronsted Lowry acids are just called Bronsted acids. What does it do when it turns into its conjugate base? In order to turn into its conjugate base, yes? It has to donate an H+. So this H+ is going to go off somewhere else. Yes? And HCl is going to turn into its conjugate base. Tell your partner, what is the conjugate base of HCl? It is Cl-, yes. Because we have to remove not only a hydrogen, but we also have to remove a plus charge. What about HSO4-? Yeah, it's going to be SO4. We remove that hydrogen, and it becomes 2-. How about HPO4 2-? It becomes, yes, PO4, the H is gone, and then it's 3- because we lose a positive charge. If a chemical is acting as a base, so if we have a Bronsted Lowry base, it's going to turn into its conjugate acid, and it's going to do that by a hydrogen being donated from somewhere, probably from an acid. Okay, not probably, certainly from an acid. A hydrogen's going to come in. So who is the conjugate acid of CO3 2-? Tell your partner. Actually, you know what? See if you can fill this in without me telling you. See if you can fill it in. Maybe use pencil if you're unsure. And then you can always change it later if you need to. That was quite something. So who is the conjugate acid of CO3 2-? Yes, that's going to be HCO3, and its charge, sorry, minus, because it also gains a positive charge when it gains that hydrogen. The next one is a little bit tricky. If you wrote HCH3COO, that is not incorrect, but it is better to write CH3COOH. Do you remember that our organic acids, the detachable proton, this one here, the detachable proton goes on the carboxylate group. If you are taking biology, that might be a good term for you, the carboxylate group, yeah? And it will turn into the carboxylic acid group, which is COOH. So the carboxylate group is COO minus, and it turns into COOH. Like I said, if you're taking biology, that might be important to you. For chemistry 12, it's not particularly important. It might also be important, though, if you carry on for university chemistry, okay? So, given the choice, if you have a COO, put the H on the end. What about our HPO4 2-? What do we get? The conjugate acid is H. 2PO4 minus. And HCO3 is? Conjugate acid is H. 2. CO3, what's its charge? -1 plus +1 is 0. So it just has no charge whatsoever. Now, one thing you might notice, if we sort of zoom out a little bit here, is that we have HPO4 is given as an acid, but it is also given as a base. Do you remember the word that we use for such substances which can act as either Bronsted Lowry acids or as Bronsted Lowry bases? Tell your partner, see if you can remember. You guys remember it? Starts with an A. There was a picture to help you remember. Yes, Amphiprotic, because it can do both. Where else have you heard the prefix amphi? Amphibians. And where do amphibians live? Land and water both. Yes? So amphi means both. And if you didn't appreciate the picture of the little frog, go back and appreciate it, because about 5 years ago, I spent a lot of time looking for the perfect image of a frog to make it memorable. Okay, so just go and appreciate that. So chemicals that can act as either an acid or a base are called amphi, which means both. And then they can either donate a proton or they can accept a proton, so they are amphiprotic. Amphi meaning both. Same root probably as ambidextrous. Okay, it's gotten, it's changed a little bit over time from amphi to ambi. But if you're ambidextrous, you can use both hands. Okay, and then protic. Both accepts and donates protons. So another definition of amphiprotic, you'll notice I'm getting you to write it a lot. That's because you do need to be able to write it and spell it and all of those good things, okay? A substance which can act as a what donor? Proton. And what is a proton? H+. Or it can act as a proton acceptor, which is H+, of course. And I didn't bother putting the frog in here again, but I did give you amphi, Greek, meaning on both sides. Amphibians can live both on land and water. Now, if you were going to go and recognize an amphiprotic substance, so if I just gave you a chemical and says, is it amphiprotic? One thing that it has to have is a hydrogen. How can you donate an H+ if you don't have an H? It is impossible, yes? So, an amphiprotic substance has to have a hydrogen, and almost all amphiprotic substances also need to have a negative charge. That negative charge allows them to accept that positive hydrogen ion. There is a notable exception to that second rule, and that exception is water. Water is amphiprotic, and it can either accept a proton or it can donate a proton depending on what it needs to do, even though it lacks a negative charge. Okay, but most of the time you will have both a hydrogen and a negative charge, and it will be amphiprotic. Back to our other notes. Bases produce OH minus in water, yes? How does a Bronsted Lowry base produce OH? So for example, NH3, ammonia, is a Bronsted Lowry base. And I defy you to find an oxygen in that compound. Yes? It's just not there. So where is this hydroxide coming from? It's coming from water. Yes? Because the Bronsted Lowry base reacts with water to produce OH minus. So NH3, which is aqueous, it is dissolved in water as an intact molecule, okay, floating around there. H2O, which is a liquid. And because this is the base, what must water be acting as here? It must be acting as the acid. So the hydrogen is going to move from the water to the ammonia. And what will our products be? Yes. NH4 plus and OH minus. In our reverse reaction, tell your partner, who is the acid and who is the base in the reverse reaction? Who's the Bronsted Lowry acid? They both have H's, oh dear. But who is giving the proton to whom in the reverse reaction? NH4 is giving the proton to hydroxide. And so for the reverse reaction, NH4 is acting as the acid and OH minus is reacting as the base. So one thing you're going to notice about this particular reaction and all acid-base equilibria is that on each side of the equilibria, there has to be both an acid and a base. You cannot have two acids on one side of the equilibrium. It doesn't make any sense. Yes? I've left some space for a reason. Who are the conjugate acid-base pairs? In the above equilibrium. I'll give a minute, and then we'll come back. So there's going to be two conjugate acid-base pairs. Tell your partner who is one, what two things make one conjugate acid-base pair and what two things make the other conjugate acid-base pair. So who is one conjugate acid-base pair? Yes? NH3 and NH4 plus, and our other one, H2O and OH minus. And we can show them, we'll often write it this way in the equation. We'll often go like this and say, oh, look, here is a conjugate acid-base pair. And here is our other conjugate acid-base pair. What do you notice about the two members of each pair and their position to each other relative to the reaction arrow? What did I mean by that? Yeah. So take a look at this. Where are they relative to each other and relative to the reaction arrow? So if we look at H2O and we look at OH and we look at the reaction arrow, what can we say about those two? They are on opposite sides of the reaction arrow. NH3 and NH4 are on opposite sides of the reaction arrow. So your conjugate acid and base pairs, the two members of the conjugate acid-base pair will always be on opposite sides of the reaction arrow. That shouldn't be surprising, because how does an acid, if I'm an acid and this is my hydrogen, how do I turn into my conjugate base? I have to react, yes? And I go through the reaction, now I've turned into my conjugate base. So they have to be on opposite sides because they turn into each other by reacting. Okay, back to 4.1. And now we are going to take a look at our acid table. So you are welcome to look at this one here. It is the second page. And if you have a color printer at home, it wouldn't be the worst thing in the world to like print out a color copy of this because it's nicely color coded. All of our acids are in what color? Red. And all of my bases are in blue. So on which side do we find the acids? On the left-hand side, and look, it's labeled acid. And on the base side, it's labeled base. And the other thing that you'll find on here is the Ka values. We will be using those a little bit later on, but you'll notice that up at the very top, the Ka values are just defined as being very large. If a Ka value is very large, what does that mean? It means the equilibrium sits where? Products or reactants? So if KEQ, Ka, which is the KEQ for an acid, okay? If Ka is very large, what do we have a lot of? Products. And the products in this case are the dissociated ions, yes? The reactants is the intact acid molecule, okay? So when we say very large, we basically mean that the thing has dissociated completely. So up in that gray zone, what do you notice about all the arrows up in the gray zone? Okay, they're all one-way arrows. So HClO4 will only turn into its conjugate base ClO4 minus. ClO4 minus is actually, it is the conjugate base of HClO4, but it is too weak to take its proton back. So even though ClO4 is on the base side, and even though it is the conjugate base of HClO4, it is actually too weak to act as a base. And that's why those are yellow instead of red or blue, because ClO4 is certainly not an acid, is it? No, not an acid, doesn't have a hydrogen, but it is too weak to be a base. It cannot accept a proton. So it is neither an acid, it cannot really act as either an acid or a base. So it would just be neutral, okay? But it is the conjugate base, so we put it on the base side. And in fact, if you had a different solvent than water, you might be able to have it go backwards. But we won't talk about that too much because it mostly just confuses people, myself included, okay? Because it's been a long, long time since I've studied that because we never touch on it in AP Chem or Chem 12, none of that. So I've forgotten most of it. It kind of rings a bell, but it's a little off. Okay. Now, once we get out of this area, oh, and by the way, anything that dissociates completely is known as a what? What kind of acid? Strong acid. Okay, so up here in this gray zone, these are our strong acids. Their conjugate bases are too weak to act as bases. So the conjugate bases of strong acids are too weak to act as bases. Now, after we get out of that gray zone, now we get into the main body of the table. And we no longer have strong acids. Now we have instead the weak acids, which means that they dissociate somewhat. Yes? So if I had a whole bunch of pens, this was so much better when I had the overhead projector because I would just put them on there. If it was a strong acid, all the hydrogens would dissociate. Yes, if the caps are the hydrogens. So this would be a strong acid. We would have all of these floating around separately, and we'd have all of these floating around separately. In a weak acid, most of the acid is floating around in its undissociated form. Yes? Most of it, and I can't make them all move because I don't have like 16 hands. Yes? And there's only a little bit of it that is dissociated. Okay? And that's why we call them weak acids. They form an equilibrium. Every time one of these gains its cap, another one dissociates. Yes? Very, very analogous to, well, any other equilibrium, the solubility equilibrium. Every time one dissociated, another one reformed. The only thing that's different now is that our ionic crystal was not in solution, whereas this one, our intact molecules are actually dissolved. They're actually aqueous. So, in our table, we have a small area at the top that includes these strong acids, and then we have the weak acids, and then we have down at the bottom another gray area, gray zone. And you'll notice once again, which way do those arrows go? They are one directional, yes? But this time they are one directional going to the left. So down here, these are our strong bases, because remember, bases are on the left. So our two strong bases are O2 minus and NH2 minus. If you have the purple chart, I've put a third one on there, okay? But that's just kind of neither here nor there. Ammonia, NH3. See it here? Is ammonia a strong base? No, because it is not on the base side. Bases are over here, yes, bases, and acids are over here. So technically, in this case, NH3 is an acid, quote unquote. Is it any good at being an acid? Is NH3 ever going to be able to donate a proton and become NH2? No, because this arrow only goes that way. So NH3 is too weak to act as an acid. So ammonia is not an acid. It's not a weak acid. It's not a strong base. People are always tempted, because it's in that gray zone at the bottom, to say, oh, ammonia, a strong base. I know it's a base, it's in the strong base area, but it's not. Only these two are the strong bases. Where you will find ammonia is up in the middle of the weak base section. Yes? So you can see it kind of right there. Yeah? So ammonia is a weak base. It can accept a proton and become NH4+. So that's really all there is to this table for now. We will come back and visit it a lot. Just a few little notes at the bottom. The larger the Ka, the stronger the weak acid. This leads to terrible wording, like these down here are weaker weak acids. Yes? The weaker weak acids, a smaller percent of the acid, HA, is dissociated. H++, minus. So if you have a weaker weak acid, not as much of it is dissociated or ionized. As you go up the table, guess what? You have stronger weak acids. Oh, isn't that lovely? But what it means is that a larger percent of the HA molecules are dissociated into H+ and A-. The base side of the table works just like the acid side of the table, except that it is virtually, it's pretty much just upside down. Yes? You find your strong acids at the top, your stronger weak acids, and then at the bottom you have your weaker weak acids, and then you have things that are too weak to even be acids at all. With the bases, where to go? There we go. Okay. With the bases down at the bottom, we have the strong bases. And then we have all our weak bases as we move up, but they get weaker and weaker and weaker and weaker and weaker until we finally hit those bases that are so weak they can't actually act as bases. All right, so that's our table. How are we doing for time? 10 more minutes. Excellent. I know you're like, oh my God, can we not be done now? But no, we can't. Okay, blah, blah, blah. There we go. Okay. Is HSO4 minus amphiprotic? So this is on the page afterwards. The little text at the top is just what we've been talking about, okay? What were the two things we said that a substance needs to be amphiprotic? Yes. It needs to have a hydrogen and it needs to have a negative charge. So by that definition, HSO4 is looking promising, yes? It has an H, it has a negative. However, let's go and look at our data booklet. Okay. So let's look here. There's HSO4, and that's on the left-hand side of the table. So HSO4, and it's in the weak acid section, and we've got an arrow going forward. So is it able to act as an acid? Yes, it is. Acid, yes. Can you find HSO4 on the other side? Yes. Right up here, yes indeed. It is on the base side, but remember, what do we know about these guys here? They are too weak to act as bases from here to here. So, although HSO4 physically meets the criteria, in actual fact, it cannot act as a base. So HSO4 is an exception in that it is not amphiprotic. Every other one though, let's go look at a couple. Oh look, here is a substance that has an H and a negative, HC2O4. And it has an arrow going that way, so we would say base. Yes. Can you find HC2O4 minus on the acid side? Oh, there it is, down at 6.4 times 10 to the negative 5. And we've got that hydrogen and we've got the negative. We say, oh, and it is able to go that way. So can it act as an acid? Yes. Okay, so you'll see anything that's within that white area is A-okay as long as both substances are within there. Yeah, so that's it for those. 5 more minutes. Excellent. Keep going. And remember, if you're dying right now, you can always come and watch the last 5 minutes of this if you've like totally like zoned out on it because your brain is dead. Because mine is almost dead. But okay. Yeah. There we go. Now, let's take a look at our amphiprotic substance. This is example number 2 on page, I don't know which page. Oh, that's electrochemistry. That's not going to help me. Example number 2 on page, oh, it doesn't have page numbers on it. Well, that's unfortunate, but anyway, okay, fair enough. You can number them yourself if you want. At any rate, how do we know HCO3, it's got that hydrogen and it's got a negative charge, so it is amphiprotic. How do I know whether it's going to act as the acid or the base in this reaction? Yes. Exactly. It has to act as the acid because PO4 minus does not have a hydrogen, so it cannot act as an acid. PO4 minus has to be the base because it's got no hydrogen, which means that HCO3 minus is acting as an acid. So if you have an amphiprotic substance and it's with a base, it's going to act as an acid. If it's with an acid, it's going to act as a base. And we'll pick this up after your test tomorrow. I will be here for flex time tomorrow. Okay?